Strip away high-level programming abstractions, and malware is just electrical states. Assembly language is the literal, human-readable representation of those raw machine code bytes. Each assembly instruction, or mnemonic, directly corresponds to one or a few bytes of machine code that the CPU executes natively. A disassembler takes those opaque hexadecimal bytes and translates them back into readable text. This direct translation allows an analyst to systematically reconstruct the original program logic, even when all source code and debug symbols have been intentionally stripped away. The x86 instruction set is massive, but you do not need to memorize the entire manual. Roughly 20 core instructions account for the vast majority of what you will actually read in malicious binaries. By converting high-entropy hex bytes into a structured list of instructions, the disassembler provides the raw material needed to map out a program's internal logic. We use the x86 Intel syntax, the standard for tools like IDA Pro and x64 DBG. It follows a strict rule: mnemonic, destination, source. The destination always receives data, and the source always provides it. Data flows strictly from right to left. For example, MOV EAX 5 takes the constant integer 5 and copies it directly into the EAX register. Be aware that tools like GCC and GDB default to AT&T syntax. That format reverses this destination source order, causing severe misinterpretations if you are not checking your tool settings. Every x86 instruction operates on 0, 1, or 2 operands, and these operands take one of three forms. An immediate is a constant value encoded in the instruction itself. A register refers to the CPU's internal storage for the fastest possible access. Memory targets a specific RAM address, always denoted by brackets to indicate dereferencing. The x86 architecture imposes an absolute constraint on memory access. A single instruction can contain at most one memory operand. Because of this rule, MOV EAX EBX is an invalid operation. You cannot copy data directly from one memory address to another. The data must be routed through a CPU register first. Internalizing these strict syntactic and operand rules is required before you can decode any higher-level algorithmic behavior. The MOV instruction is statistically the most common operation in any compiled binary, strictly responsible for copying data from a source to a destination. Contrast this with LEA, or Load Effective Address. LEA calculates a mathematical memory address and loads that address, not the value stored inside it. Compilers frequently abuse LEA as an arithmetic shortcut to perform quick math without modifying CPU flags. Stack memory is managed dynamically. Push subtracts 4 from the current stack pointer, ESP, writing data into that newly allocated address. The reverse is POP. It reads the value from the ESP address, then adds 4 to the ESP register, erasing the allocation. Standard arithmetic operations include add, sub, inc for incrementing by 1, and dec for decrementing. Crucially, these operations actively update the CPU's internal status flags based on their mathematical results. The mul instruction performs an unsigned multiply. Because multiplying two 32-bit numbers can create a 64-bit result, it splits its output across two registers, storing the high bytes in EDX and the low bytes in EAX. Mapping these specific data flows and arithmetic manipulations provides the initial outline of an algorithm's true intent. When analyzing cryptography or hashing routines, you will encounter the standard bitwise operations, and, or, not, as well as SHL for shift left and SHR for shift right. One bitwise operation is ubiquitous, XOR EAX EAX. It generates exactly 2 bytes of machine code, 31CO. Doing the same with MOV EAX 0 takes 5 bytes. Compilers utilize this method to zero out a register, specifically optimizing for code density. To evaluate conditions, x86 uses CMP and test. CMP computes a subtraction, discards the numerical result, and sets the CPU flags. Test does the same thing, but computes a logical AND instead. These flags dictate execution branching. Unconditional control flow happens via JMP to jump directly to an address, call to push a return address and jump to a function, and RET to pop that address and return control. Conditional jumps, like JE for jump if equal, or JNZ for jump if not 0, rely entirely on the processor flag set by the preceding instruction. These jump instructions act as the intersections of the code. By tracking how flags influence these branches, we can map the various execution paths available to the program. Compilers generate highly standardized instruction sequences to manage stack memory at the beginning and end of discrete functions. These are known as prologues and epilogues. The standard prologue sequence looks like this. Push EBP saves the caller's base pointer. MOV EBP ESP establishes the fixed base pointer for this new frame. Finally, sub ESP 0x20 dictates the strict size of the local variable space reserved for this specific function. If you see an abnormally large subtraction value, like sub ESP 0x400, that immediate 1024-byte allocation reveals a large local buffer, flagging a potential buffer overflow target. The epilogue reverses this exact process. MOV ESP EBP instantly discards all local variables by resetting the stack pointer. Pop EBP restores the color state, and ret returns execution control. Because compilers generate these literal byte patterns consistently, recognizing them visually is the most efficient way to isolate discrete function boundaries within a raw, unmapped binary. In a 32-bit stack frame, memory structure is strictly defined. Above the EBP boundary are the caller's arguments, located at EBP plus 0x08 and EBP plus 0x0c. Below EBP are the current frame's local variables, located at EBP minus 0x04 and EBP minus 0x08. This precise memory geometry is not arbitrary. It is standardized across virtually all 32-bit Windows code compiled with Microsoft Visual C++ or GCC. Internalizing these specific EBP offsets allows you to immediately map variables and identify function arguments in a debugger, completely bypassing the need for manual address calculations. Once you understand individual instructions and stack architecture, you can transition from reading isolated lines of code to recognizing higher-level structural idioms. This snippet features a tight loop utilizing an XOR instruction against a static 0x55 key, followed by an INC and CMP. This signifies a localized decryption routine. Your objective: extract the key and buffer address to statically decrypt the payload without executing the malware. In a standard CDEC Windows API call, the program pushes a file path, a read flag, and then calls create file A. Reading these sequentially pushed values reveals the function's exact target, whether a dropped file, malicious registry key, or command and control URL. Treating these instruction blocks as cohesive, predictable idioms accelerates your triage and reverse engineering process. Malware authors know analysts use these techniques, so they build anti-debugging mechanisms. The malware will actively scan its own memory space in real time to detect the presence of debugging tools. The most common detection is a software breakpoint scan, which looks for the 0xCC opcode injected by standard debuggers. The countermeasure is simple: utilize hardware breakpoints. They use the CPU's internal debug registers to monitor execution without modifying the binary, evading detection. Technical fluency in x86 allows an analyst to ignore the high-level signals the malware sends to the operating system and focus instead on the immutable logic executed by the processor itself.